We just finished doing a lab demo involving the alkali metals and the alkaline earth metals, the two reactive groups of metals on the periodic table. Those groups of metals are so reactive that they're not even found in their pure forms in nature. They're always bonded to other things. In this lesson, we're going to be looking at elements that can be found in creation in their pure forms, the transition metals. The other important thing to know about the transition metals is we use them for all sorts of things. We use them to build structures, we use them to manufacture products, and we can do that because they have all of the awesome characteristics of metals. They're great conductors, they're solid, they are malleable and easy to shape, but also they are not very reactive with other elements. Let's get started observing the transition metals by taking a look at where they are in the periodic table. Remember, the transition metals are in that unpredictable group right in the middle of the periodic table of elements. And what I mean by that is that the transition metals can form ions with anywhere from a 1+ to all the way up to an 8+ charge. Now, those extreme ends don't usually happen. Most of them form 2+ ions. Some of them can form multiple varieties of ions. We're going to take a look at one of these transition metals. The first atom we're going to look at in the transition metals section of the periodic table is a copper atom. And as we look at the inside of this atom, you'll notice that there is one electron that's far away from the nucleus. However, when I show you all of the electrons that can participate in the sea of electrons metallic bond, there's a whole bunch of electrons that are available to bond this metal together. The reason that the transition metals do this is because there's not a lot of difference in the energy between the outer electrons and the electrons just underneath. So that's one of the things that makes the transition metals behave the way that they do. They can share several electrons in the sea of electrons between atoms. It's not necessarily just the outer electrons. So what that's going to cause to happen with atoms like copper is they're going to bond together very, very tightly because there's so many electrons in the sea of electrons. Now this is a little bit exaggerated. I show an 11+ charge because technically there are 11 electrons that are available in copper that are able to potentially help bond these together. But rarely will all 11 electrons participate in the sea of electrons. It's going to be some number lower than 11 electrons. So this is what copper looks like at the atomic level, very tightly bonded together. Some properties that it has is that it's very dense, it has a high melting point, and it's a hard metal because it's so strongly pulled together by those many electrons in the electron sea. And then finally, because there's so many electrons to remove to cause a bond to form, there's at least 2 for copper, it's a very stable substance. It doesn't react easily with other atoms. Let's take a look at another atom from the periodic table that's a transition metal. We're going to take a look at zinc because it's the other metal we're going to be observing in this lab. As I look inside this zinc atom, I see there are 2 electrons far away from the nucleus. And actually, zinc is sort of unique. The metals underneath zinc behave this way in the periodic table as well. Zinc really only contributes 2 electrons to the metallic bonds holding it together as a crystal, and therefore zinc doesn't have as high a density and it doesn't have as high a melting point as some of the other metals do. During this lab, we are going to take zinc atoms and we are going to use them to coat the outside of copper. We're going to take a penny, we're going to put it into a soup of hot zinc dissolved in water. There's going to be zinc chloride or zinc acetate, and there's going to be zinc metal. So we're just going to make this soup of zinc ions in really hot water, and those zinc ions are going to deposit themselves on the outside of the copper penny, like you see in this picture. Now here's what's going to happen. If you remember back to the reactive metals lab, we saw reactive metals undergoing chemical reactions. They were giving up electrons, bonding to atoms in different ways, forming completely new substances. That's not going to be the case with the transition metals. The transition metals are so unreactive that even when we put them together and heat them up, put them under high stress conditions, they're not going to undergo a chemical change, but a simple physical one. what's going to happen is some of the zinc atoms are going to mix into the copper, and some of the copper atoms are going to mix into the zinc, and we're going to end up with a solution or an alloy known as brass. We're going to see that the silver-colored, zinc-coated penny is going to change gold at the end because the atoms aren't chemically reacting. They aren't changing to completely different substances. They're just going to mix together. Again, the transition metals are extremely stable because of the way that their electrons are. And because they're so stable, we're going to notice that there's not going to be a chemical reaction, just a mixing together of atoms in a physical change. So here I have the setup for the transition metals lab. I have my zinc acetate. I actually use zinc acetate instead of zinc chloride because it gives off less fumes and is a little bit easier to take. I have my zinc acetate boiling in this very dirty beaker that I have dedicated to the task of boiling zinc acetate. It's very, very difficult to clean this out afterwards. And over here I have my pennies, which I've been soaking in a solution of salt and vinegar to try to remove any dirt or crud from the outside of them. You're supposed to use pennies that are shiny, but made before 1983, which just is very, very difficult to find. So I find that shiny, newer pennies do the job just as well with the copper content that they have. They are made of some copper, but they're made up of a lot more zinc than they used to be. I'm going to take these pennies and I'm going to put them into this boiling bath of zinc acetate dissolved in water with zinc metal on the bottom. The reason why I'm doing this is because they're just going to be bathed in ions of zinc, and those zinc ions are going to plate themselves to the outside of the penny. I'm going to stir this really well to make sure that the pennies get mixed into the zinc metal on the bottom very, very evenly. I also want to make sure that the surfaces of the pennies aren't touching each other, because if their surfaces touching each other, they're not going to get coated. After a little bit, we'll take these pennies out and see if they actually get coated in zinc metal. It's only been a couple of minutes and my pennies have already started to take on a silvery color. They're only finished when they've taken on a complete covering, so I'm going to put this one back in. Now with other elements on the periodic table, if you boiled them at this temperature, because the temperature is so high and you're adding so much energy, it would force them to react. But because the transition metals are so unreactive, they are able to resist corrosion and chemical reactions, there's not actually a chemical reaction going on here. It's not like the copper on the pennies is wearing away. It's just being plated with zinc. It's still zinc and it's still copper, the same materials that were there before. And there we have it. These pennies have been completely coated in zinc, so they have this nice, shiny, silvery color. They are just vibrant, shiny silver. You can leave them this shiny silver color if you like, or you can put them back on the hot plate for a minute and watch very carefully to see the moment that they completely change color. The moment they change that coppery color, you need to take them off the hot plate and douse them in a container of cooling water, and then you should see that they change to a vibrant gold color. What you've just done is you've mixed together atoms of copper and zinc to make brass. Let's do just one more. I'm going to take this silvery, shiny penny and place it on the hot plate so it's in contact with the heat for just a few seconds. I'm going to watch very carefully to see the moment that the penny changes back from silver to sort of a coppery color once again. The moment the entire penny is coppery, I douse it in the water, and we have a gold colored, actually a brass penny.